Hello students, and welcome to your final online lecture and experiment for the semester. In today's lab, we will talk about resonance and RLC circuits. And additionally, we will talk about what's known as the quality factor of resonant circuits. So let's define resonance. So resonance describes the amplification that occurs when a driving frequency is in harmonic proportion, or it's an integer multiple to a natural frequency of an oscillating system on which it acts. So this means that if a system is oscillating and you're putting energy into the system, if the frequency of the energy that you're putting into the system is the same as the natural frequency that the system wants to oscillate at, then these are said to be in resonance. Okay? So let's write that down. So the amplification that occurs when a driving frequency is in harmonic proportion to a natural frequency of the oscillating system on which it is acting. So in resonance, two systems are coupled in such a way to facilitate efficient energy transfer between them. So when a driving frequency is applied at the resonant frequency of the system will oscillate at a higher amplitude than the same frequency applied at a non-resonant frequency. So to have a visual representation of this from classical mechanics, think of a pendulum swinging, or you can think of someone on a swing. It's oscillating back and forth. Right? If the person that's on the swing wants to increase their amplitude, they could have a friend push them. Right? Now that friend provides energy to the system at various intervals or pulses. So you can think of it as the driving force. Okay? So as your friend swings back and forth, if you want to increase their amplitude, you have to push them with the same frequency that they are swinging. So on the upswing, as soon as they reverse direction, you want to apply that push, and that will increase their amplitude. Now for a pendulum, the natural frequency omega naught is equal to the square root of G over L. So it is proportional to the square root of gravitational constant and inversely proportional to the square root of the length of the pendulum arm. You may have covered that in classical mechanics. So when you're pushing your friend forward at the same frequency that they're swinging, this increases their amplitude because there is a constructive interference happening. If, for instance, your friend is swinging back toward you and you push them forward before they have had a chance to reverse their direction, you are now in destructive interference with your friend that's swinging, and you will no longer amplify their swinging, but you will actually reduce the amplitude of their swinging, and you might even stop their swinging altogether depending on how hard you push them. So we can write, resonance is also the condition of perfect constructive interference. As perfect as we can get in the real world. Constructive interference. Okay, so how does this relate to our electromagnetic systems in our circuits? So it's easy to picture what's oscillating in classical mechanics. You can have a pendulum that's swinging, you can have a spring that's oscillating up and down. In electromagnetism, it is actually a little more abstract. So let's draw a resonant circuit. So a resonant circuit comprises an inductor with inductance L, capacitor with capacitance C, and depending, it has a resistor of resistance R. So the LC component gives rise to the natural oscillations, while the resistor acts as a damper to these oscillations. So theoretically, if you got rid of the resistance, the LC resonant circuit should oscillate forever, but it's not the real world we live in, so we're going to use resistance here. Alright, so remember we've learned that capacitors store energy in their electric field. And conversely, inductors store energy in their magnetic field. Okay. So in RLC circuits, we connect these components together. Maybe introduce a little resistance here. And what happens is, first, the capacitor, or you can think of the capacitor being charged first and storing that energy in its electric field. Then once the system is set into motion, the capacitor will discharge the current into the circuit, which means it goes into the inductor. So remember, as the inductor goes through a change in current, it will generate a magnetic field. So the capacitor continues to discharge its energy into the circuit, and this will continue to induce a voltage and create a magnetic field in the inductor. Now the energy is in the magnetic field of the inductor. So since the induced voltage of the inductor acts to oppose the change in current and produce a voltage equal and opposite to that which caused it, now current will return to the rest of the circuit and charge up the capacitor. So this is where the oscillating behavior comes from, is the energy that's coupled in the electric field of the capacitor with the magnetic field of the inductor, and they oscillate back and forth like this. Now it's easy to see the oscillations of your friend on a swing, but this happens at 1,000 to 1,000,000 times per second. It's very high frequency oscillations here. Alright, so the natural frequency of a resonant circuit, an RLC circuit, is given by 1 over square root L times C. So if you want to know what the natural or resonant frequency of an RLC circuit, just perform this calculation. So the most common application of RLC circuits is tuning in radio transmission or receivers. So the ability of this circuit to resonate at a certain frequency allows it to select and tune into certain frequencies. So you can imagine turning that dial on your radio, you're actually changing the resonant frequency of the circuits, and that is selecting different radio stations in your device. So now let's talk about the quality factor, which is where the experiment lies. So the quality factor determines how selective your circuit is. So if you imagine we have a spectrum of frequencies, say we have 900, 950, 1000 hertz, etc. So this is frequency. And you have different amplitudes of these frequencies, say in an amplitude modulated signal. And you have a resonant circuit that's resonant, say at 1400 hertz. You can have a resonant circuit with a high quality factor. It's very selective. Or you can have a system that resonates at the same frequency but has a lower quality factor. This is Q2. So today in the experiment you'll be measuring the quality factors of various RLC circuits and then checking that against the theory. So the quality factor is given by Q equals omega naught, which again is the natural frequency, over delta omega, which is called the bandwidth. So in the bandwidth, you look at the width of this peak at 70% of the maximum intensity. This is delta W. So in today's experiment, we'll be measuring the quality factor of various RLC circuits by measuring the current. So we look at the driving frequency, omega, and we look at the current, say milliamps, and we sweep the RLC circuit through a range of frequencies and measure the current. And then the resonant frequency can be obtained from the peak intensity of the current. Similarly, the bandwidth can be measured by measuring the width at 70% of max current. So there's a small proof for why the current peaks at the resonant frequency, which involves reactance. So let's go over here. So if you remember the reactance for an inductor, which is the resistance to a flowing current, we have chi L, which is the reactance versus frequency, and it's proportional to frequency, the reactance. Because reactance is equal to pi f L. For the capacitor, or capacitive reactance, we have the inverse behavior. Chi sub C, or capacitive reactance, is inversely proportional to the frequency. So you get something like this. Now in an RLC circuit, we have both components, so all we have to do is combine these graphs. So we can superimpose these curves and say this is the capacitive reactance. So notice there's a point where they intersect here. So at frequencies below this point, we get a dominance of inductive reactance, and in frequencies above this point, we get a dominance of, I think I had that backwards. So below this point, for frequencies below this point, the inductive the capacitive reactance dominates, and above that frequency, the inductive reactance dominates. Okay? So, recall that the impedance was equal to square root of resistance squared plus the reactance squared, total reactance squared. So the total reactance is given by chi sub L minus chi sub C. So notice that when the reactance is equal here, we minimize the reactance. So chi sub L minus chi sub C, if they're both equal, that is 0. And this entire term goes to 0 in the impedance calculation. Therefore, our impedance is just equal to resistance. So current is maximum in resonance because the impedance to current or flow of charge is actually minimized at that point. So I think that's it for the theory, and now we'll just jump right into the experiment. Thank you.